Hi, let's understand business. In this session, we shall be discussing about the quality control charts for attributes. Before we start discussing about quality control charts for attributes, let us take a quick recap as to what do we understand about the quality control charts. Basically, a quality control chart consists of various points representing the measurements of a quality characteristics within the sample, which is taken from the sample at different places or different times. Then we have a center line, which is the mean or the standard uh, to which the particular quality characteristics has to meet. We have the upper and the lower control limits. The upper and the lower control limits are the threshold beyond which the process or the output is quite unlikely, or where we can definitely say that the process has gone out of control. Apart from these, in a quality control chart, we might also have the upper and lower warning limits, which are drawn at around plus and minus two times the standard deviations from the center line. So basically, a quality control chart would have the center line, which is the standard to which we have to adhere for the quality standard of the characteristics, the various points representing the samples which we have taken from the population. We would have the upper and the lower control limits beyond which the process is unlikely, or the process is unfeasible, or the process has gone out of control. And we may also have the warning limits, which is an indication that perhaps we should take some corrective action on the quality or the aspect to control the quality of the product. Now, coming to the quality control chart for attributes. The quality control chart for attributes is drawn for those quality parameters which cannot be measured, or which just give us whether the quality of a product is good or bad. That's why we call it attribute. It cannot be measured. There's no dimension to whether it could be controlled. The attribute is such that would determine whether the quality of a product is good or the quality of the product is bad, whether the quality is acceptable or it is not acceptable. So there are three types of quality control charts for attributes. First and foremost, we have the fraction defective chart, which is also called the P bar chart. Then we have the NP chart, or the number defective chart, and finally we have the number defective per unit chart, which are used at different conditions, under different conditions, which we would be discussing in the next slide. So when it comes to the quality control chart for attributes, we will be discussing the three different kinds of chart. Firstly, we have the fraction defective chart, or the P bar chart. Then we have the NP chart, or the number defective chart, and finally the C chart, or the number defective per unit chart. All these three charts are used in different scenarios. For example, when the size of the sample is uniform and the sample is significantly large, or the number of defective pieces in the sample are significantly large, we use the fraction defective chart, which tells us what fraction of the sample is defective. Supposedly, the sample size is uniform, but the number of defectives in the sample are not so big, not so many. So we use the number defective chart. Finally, when the sample size is not uniform, we use the number defective chart, and also where in a single sample there could be more than one defect, we use the number defective chart per unit, or the C chart. Now we shall be discussing each of these charts separately. Among the quality control charts for attributes, firstly we shall be discussing the fraction defective chart, or the P bar chart. When it comes to the quality control of attributes, the quality parameter which we are trying to control is such that it cannot be measured in dimensions. That is, whatever we can say about the quality parameter is whether it is good or bad. There cannot be any measure about it. How good or how bad we cannot determine. And in such situations, we use these quality control charts for attributes. Right. So the objective of this chart is to control the portion of defective with respect to the specific quality attribute, and this control is done even when the attribute standards are not known. So when we do not know the standards and we have to control the quality of a product, of the attribute of a product, this is done through inference. So it is inferred by finding the average number of fraction defectives, that what fraction of defectives is okay or it is acceptable within a sample. We find an average, consider that average as a mean or a standard. We try to control the quality. This chart is used to control the general quality of component parts, right? As mentioned, that in fraction defective chart we try to control the quality through inference. So basically what we do is we try to check whether the fluctuations in the product quality are due to some chance causes or due to some assignable reasons. We try to control or take care that there should not be any assignable reasons for the quality to go bad. To control the quality through fraction defective chart, first and foremost, we take the help of the average number of defectives, or the average fraction of defectives within a sample, usually denoted by P. And based on that, we have the limits for the chart, the upper control limit and the lower control limit, which is given with the formula as shown here. We have the formula both for the upper control limit, which is P plus 3 times P into Q upon N under root. I will explain this formula with the help of an example also. And similarly, we have the lower limit where it is P minus 3 times PQ upon N whole under root. So where we have P is the average fraction defectives within a sample of the sample size. Q is the average fraction non-defectives, that is Q is 1 minus P. If the fraction of defectives within a sample is P, then Q is the fraction of non-defectives, and N is the number of items in each sample. So to understand it better, let us take the help of a simple example. So let us try and understand the fraction defective chart or the P bar chart with the help of an example. The example being that a quality controller examines a sample of 1000 items each and finds that the number of defectives are as follows. So what we have to do is we have to draw a control chart for the sample. Here if you see, we have samples numbered from 1 to 20. In the first sample, 215 number of defective pieces are there. Similarly in second, 227, in the third, 220, in the fourth, 180, and so on. So we have 20 samples of 1000 items each, in which the number of defective items has been tabulated in this chart. What we have to do is we have to draw a quality control chart and determine whether the quality of the product, what we are getting, what we are manufacturing, is okay or not. So here we have, first and foremost, what we do is we try to find out the P bar, or which is the average number of defect. So we take the sum of all the number of defectives and divide it by the total number of samples. The total we get is 4734, and by dividing 4734 by 20, we get 236.7 is the average number of defective per sample. So to draw the P bar chart or fraction defective chart, we know that the size of the sample is 1000. The P, what we just found out, the average number of defective pieces per sample was 236.7. So the value of P we get is 236.7 divided by 1000, that is the fraction of the sample which is defective is 0.2367. With that we find Q. Q is 1 minus P, which is 1 minus 0.2367, which is 0.7633. Now applying the formula for the upper control limit. So we have P plus 3 times whole under root PQ upon N, which comes to P plus 3 times 0.01344. If you calculate the values, you will get 0.01344 as P into Q upon N whole under root, the value of that, and which comes to this and 0.2770. So this becomes the upper control limit. The upper control limit is 0.2770. The middle line or the average is P, which is 0.2367, and we also calculate the lower control limit. So the lower control limit, again with the formula what was given, P minus, in upper control limit we had added 3 times PQ upon N whole under root. In lower control limit we would be subtracting PQ upon N whole under root. PQ whole under root PQ upon N is nothing else but the standard deviation. So what we are doing is, in the upper control limit we are adding from the mean 3 times the standard deviation, and in the lower control limit we are subtracting 3 times the standard deviation. So similarly, applying the formula and putting the values, what we get is 2.6 minus, which is 0.1964. So now we have the lower control limit, the standard line, and the upper control limit. With these 3 lines we shall be drawing the P bar chart. So we have these. So we plot the standard line, which is at 0.237, which was the P bar, the upper control limit at 0.277, and the lower control limit at 0.196. On this particular chart we now plot the various points or various fractions from which we got from each of the samples to check whether the process is in control or has been in control throughout or not. For the sake of convenience, what we see here is that we have all as decimals, 0.277, 0.237 and 0.196. So let us just multiply each value with 100 or take 1/100th of, so we get 27.7, 23.7 and 19.6. So on this now we plot the various values. So plotting each of the values on the graph, this is the kind of graph what we got. So for the sake of convenience, the red line is the standard line, the green one as shown here in this particular graph is the upper control limit, and the blue one is the lower control limit. So in the first, second, third the process is in control. In fourth it has gone out of control, again some adjustment might have been done. In fifth it has gone way beyond the upper control limit, and then it has come back to the near standard in the sixth, and so on. So this is how the control chart looks like, control chart or the fraction defective chart or the P bar chart for the problem that we took, or for the question which we discussed. So this is how a fraction defective chart or the P bar chart is plotted. So now let us come to the second chart, which is the number defective chart or the NP chart. This chart is quite similar to the P bar chart or the fraction defective chart. In the last exercise what we just discussed for the NP chart, we saw that handling fractions or the decimal points was such cumbersome. Now just imagine the challenge if the number of defectives within the sample is much smaller. So we have to use a much smaller number of fraction, or the number of points after decimal 0 would be much more. So instead of using fractions, what we do in the number defective chart is that we handle the actual numbers which are defective in this particular case or in this particular chart. As mentioned, the limits for the NP chart is quite similar to the P bar chart. What you see here, the difference in the upper control limit and the lower control limit, we have the formula NP plus or minus 3 times whole under root. Now in the bracket we have NP multiplied by 1 minus P. If you remember, in the previous example we had a PQ upon N whole under root as the standard deviation. the difference in the formula in the two charts is that this formula we get is by multiplying n throughout, or the total number of units in the sample we multiply throughout. So we have a larger number to handle, and once we have a larger number to handle, it would be make more sense, and we would not get stuck in cumbersome calculations. So here again we also need to calculate the p bar, which is sigma np upon sigma n, or which we would be discussing with the help of another example or another exercise. So in the number defective chart, we have a problem where in a manufacturing process, the number of defectives found in the inspection of 15 lots of 400 items each is given below. So here again we have the lots, the sample numbers numbered from 1 to 15, and in each of these samples, which is a sample of 400 units, the number of defective units what you see is 2, 5, 0, 14, 3, and so on. So here the numbers are much smaller. The number of defectives what we are getting within the sample is much smaller as compared in the previous example where we had used the fraction defective chart. So now what we have to do here is, first and foremost, we have to determine a trial control limit for NP chart and state whether the process is in control or not. So similarly, as for the last question, here also we have to draw the control limits for the NP chart and state whether the process is in control or not. Now, apart from that, there is yet another thing which we would be discussing in this particular chart. So that is, what will be the new value of mean fraction defective if some obvious points outside the control limits are eliminated. So what you see in this problem is that you see number of defectives, mostly they are in single units, 2, 5, 0, 3, 0, 1, 0, but specifically there are two samples or two lots, which to name specifically to be the lot number 4 and lot number 9. We have number of defectives as 14 and 18, which is clearly some kind of an aberration. So we have to see whether this is within the limit, and if it is outside the limit, by eliminating these two, what is the new kind of controls that we will be getting, and what will be the corresponding upper and the control limit, and examine whether the process is still under control or not. So this question, this is a slightly different kind of a question, but we are not just looking at the basic chart, but we will also see whether there are certain aberrations which are outside the limits and which should be eliminated, and what is the process then. Maybe there happens in cases in the manufacturing process or in any process that we know that a particular lot has gone bad because of some assignable reason. So, but that sample has come and that sample is within, very much within the lots. So we are just trying to calculate whether the assignable part is there or not, or whether we can eliminate that sample, and by removing that, whether we'll get the control process in within control or not. So first and foremost, let us try and develop the trial control limits for the NP chart. The formula, as we know, is what we had mentioned. So the NP is the total number of defects in all the lots divided by the total number of lots. So we take a sum of all the lots, 2 plus 5 plus 0, whatever was given, and we had 15 number of lots, so we divide it by 15, we get, which is 66 upon 15, which is 4.4. So P, when it comes to P bar, P is sigma NP upon sigma N. Sigma N we know was 400, and the total number of defective was 66, so 66 divided by 15, which is again divided by 400, which is 0.011. So we get P bar. Putting this value in the upper control limit, we have upper control limit as the NP. Remember, in the last case we had P as the standard line. In this case, in the NP chart, we will have NP as the standard line plus 3 times sigma. So 3 times sigma, to calculate that, we have NP into 1 minus P whole under root, which comes to this, which is 10.658. So 4.4 plus 6.258, which comes to 10.658 or simply 10.7. Similarly, we calculate the lower control limit, which is NP minus 3 times NP into 1 minus P whole under root, which is 4.4 minus 3 times whole under root, which comes to again 4.4 minus 3 times 2.086, and we get the value of lower control limit as minus 1.858. Now, since this value is coming as minus, so what we will do, we will take the lower control limit as 0. So let us plot this graph. So once we plot this graph, we have this particular thing with the upper lower limit at 10.7, the center line at 4.4, and lower control limit at 0. And here we see that two of the points, which is the 4th and the 9th, which is out of control, and they are way beyond the upper control limit. So now let's go to the next part of the question. So what did we get? We got the trial upper control limit as 10.7 and the lower control limit as 0. And from the sample, what we saw, what we discussed right in the beginning at the start of the problem, that the obvious defective lots was the 4th lot where it had 14 defects and the 9th lot which has 18 defects. Now clearly, as we can see, both 14 and 18 is way beyond the upper control limit of 10.7. So these are specific aberrations, or there must be some reason why these got so many defects, which we thus need to eliminate. So to eliminate that, what we are doing, we will have to remove these two from the obvious errors, which is creating the errors within our calculation. So the P bar now becomes 66 minus 14 and 18. So these two are being removed from the total number of defects, and earlier we had the number of defects as the number of lots as 15. Now by removing these two, we'll have only 13. So the calculation, we get 34 divided by 13 into 400, which is 0.0065. Earlier it was coming 0.11. So this is the new P bar. Now putting this P bar, we again calculate the upper and the lower control limits based on the formula which we had discussed right in the beginning. So we got the P bar as 0.065, and the upper control limit accordingly would become 2.6 plus 3 into under root 2.6 into 1 minus 0.065, which is 2.6 plus 3 under root 2.6 into 0.9935, or almost equal to 2.6. So we get 2.6 plus 3 times 1.6, which comes to around 7.4. Similarly, for the lower control limit, we take the NP minus 3 times NP into 1 minus P whole under root, which would come to minus 2.2. And again, since the value is coming as negative, we shall take the lower control limit as 0. Now let us look at both these graphs with the problems. So this was our original question where there were 15 lots and each had these values. So let us try and put the values in the graph and look how it is. In the trial case, we had the upper control limit as 10.7 and the center line is 4.4. Lower control limit was 0, and in the actual, by eliminating the obvious errors, which was the 4th and the 9th lot, we got the upper control limit as 7.4, the center line as 2.6, and again lower control limit as 0. So we'll look at both these charts. So the first chart, trial control, as we had seen, with the upper control limit as 10.4, center line as 4.4, and lower control limit at 0. We had these two specific which were way beyond the upper control limit and which was making our control ineffective, the control chart. So now let us plot it, the actual, by eliminating these two. By eliminating the above two, we have a new upper control limit at 7.4, the center line at 2.6, lower control limit remains at 0, and here what we see, while these two were the initial points which were the aberrations, we still have one point which is just going beyond the upper control limit. So apart from this, the process is in control. So So we can fairly say that yes, the process within the system was within control. So this is how we control the quality of attribute by plotting these chart. So here what you would see, the numbers as you see in the number line, here we are getting numbers from 0 to 18, whatever we get. Since it is a manageable number, we use the number defective chart. Just imagine had we used the fraction defective chart, the numbers would have been way too small because everything would have got divided by 400. So it would have been 0.00 something, and which would not have been feasible. Similarly, if you remember the first question, the first problem that we discussed in the case of fraction defective chart, the numbers that we had, the number of defectives was in a few hundreds, from 200 to something it was ranging. So again, that would have been cumbersome had we used the number defective chart. So yes, both the charts can be used in either case, but we use the chart accordingly so as to get more meaningful, or so that the value what we get is more easy to handle. So after that, we'll discuss the third chart. Finally, we come to the third kind of quality control charts for attributes, which we call the C bar chart or the defectives per unit chart. This kind of chart is used where the concept of lot is not there. That is, whatever is being manufactured, it is not getting manufactured in lots of equal sizes. This chart is used where the sample is such that there is no uniform number of items which are being produced. So the limit on the control chart cannot be laid out, as the number of items in every lot varies. Or there could also be a condition where the manufacturing process is producing just a single unit and there may be more than one defects in that particular unit. So in such a scenario where there is no concept of a uniform lot, the fraction defective chart cannot be used, nor can we use the number defective chart. Because for both these cases, what we require is that the lot size should be same, or at least every item which we are producing, they should have a single kind of a defect. If there are more than one kind of defects appearing in the same unit, then we cannot use the fraction defective or the number defective chart, because then the control would be dependent on more than one variables. In such a case, what we do is, in this particular chart, we try to plot the number of defectives per unit. The unit here could be the individual, or it could also be the lot or a sample. There could be a lot of 10, the other lot could be of 5, the other lot could be of 8. So it could be of varied lots where there are certain defects if the kind of production is such that it is being produced in lots, or if a number of units are being produced. Contrarily, there could also be a situation where every time the manufacturing process is producing just a single item, and that item may have one or more than one defects. So here again we control quality based on the number of defects in a unit, and this unit could be either the individual part what we are producing, or it could also be the unique lot size which we are producing. The formula for the upper and the lower limit here is C bar plus or minus 3 times under root C bar, where C is the average number of defects per sample. We will discuss this. Let's take an example to understand this better. Let us take an example of plotting this defectives per unit chart or the C bar chart. The problem is such that there are 10 castings which are inspected in order to locate defects in them. Every casting was found to contain certain number of defects as given below. We have to plot the relevant chart and draw our conclusions, whether the process is right, whether the process is under control, how is the process happening. Right. So there are castings, 10 castings numbered 1 to 10, and each have different effects from 2, 4, 1, 5, 5, 6 and all that. So which all, how much could be acceptable and what is not acceptable, this has to be tested. Rather, the process what is being done, whether the casting is being done properly, whether some external efforts has to be done, well, whether some interventions needs to be done, that will have to be checked through our quality control chart. So what we do first is we take the average or the total number of defects that is happening. Since each casting may have any number of defects, we cannot use the fraction as mentioned earlier. So what we are doing is first we will take the average of the defects. So C, what we call is C is the number of defects. So 2 plus 4 plus 1 and so on. And since there are 10 castings, so we divide that by 10. What we get is 27 upon 10, which is 2.7. So there are 2.7 is the C bar. Now applying the formula, upper control limit would be C plus 3 times under root C. Of course, C would be the center line. So which gets 2.7 plus 3 times under root 2.7, which is 2.7 into this, which is 2.7 plus 4.9, which brings the figure as 7.6. So the 7.6 number of defect is the upper limit, which would be at the acceptable level. Again, the lower limit would be similarly 2.7 minus 4.9, which is a negative number, minus 2.2. So we will take 0 as the lower control limit. So let us plot this and plot the points to have a look. So let us have a look as to how the data looks on the graph. So we have the center line at 2.7, the upper control limit at 7.6 and the lower control limit at 0. And what we find here is that almost all the, not almost, actually all the data, all the number of defects are well within the range. Of course, the last one is going almost touching 7.6. It is 7 defects. So the process is in control, or process is under control. So this is how we plot the 3 graphs. So let us have a recap on the quality control chart for attributes. As we discussed, the quality control charts for attributes are used to control those quality parameters of a product which cannot be measured or which cannot be put in dimensions. And we discussed 3 different types of quality control charts. Firstly, it was the fraction defective chart, which was used to control the percentage of defects allowable within a sample. Then we discussed the number defective chart, which is used to control the number of defective allowable within a sample. In both these cases, there has to be a specific sample size. So wherever there is a mass production going on or wherever there is a larger number of production happening, we use either the fraction defective or the number defective based on the number of defective pieces that we are getting within a sample. If the number of defective pieces within a sample is significantly large, one tends to use the fraction defective chart. If they are not so large, then instead of fractions, we take the use of the actual numbers of how many defects are there, whether it is acceptable or not acceptable based on the process. And finally, we have the defects per unit chart or the C bar chart. What it is, this comes into play when we do not have any idea about the sample size or there is no uniform samples which can be attained. Or it could be a job shop kind of a production where based on the order the production has to happen. Maybe at times 100 has to be produced, the other times 5 have to be produced, next time maybe 30 have to be produced. So each time one gets a different number of sample. So when we need to control the defects in such kind of a scenario, we use the defects per unit chart or the C bar chart. Alternatively, wherever a single unit is to be produced and there could be more than one defect within that unit, so there again we use this chart, the third chart, which is the C bar chart or the defects per unit chart. So this is basically about the quality control charts for attributes. I hope I could throw some light on this concept of quality control charts for attributes, and for kindly write to me for your comments or queries if you have on this topic. Thank you.